Hello, welcome to the physics classroom. Today we will discuss thermal energy. You may recall that we have been using the concept of conservation of energy. Today's notes will regard how thermal energy obeys the law of the conservation of energy. Thermodynamics is the formal name for this area of study. It is the study of heat transfer, and conservation of energy in regard to heat. The basis of thermodynamics is the kinetic molecular theory. This theory states that matter, as it is composed of tiny particles, is in constant motion. As the temperature of those particles increases, or the total energy, the particles move faster, increasing their display of that in kinetic energy. It can be conceived of as many connected balls connected through springs, and the greater the energy, the more vibration and rotation those balls have in their connection with those springs. As we had been accountants of all energy in kinetic bodies in motion, we are now going to account for all energy that is present in an object as it is displayed through the motion of these molecular vibrations and rotations. In thermodynamics, we have laws. The first law of thermodynamics states that energy is neither created nor destroyed, but can be changed into other forms. This should come as no surprise, as we are familiar with the law of conservation of energy. This is a unique field that discusses, in particular, thermal energy. As such, the first law must clarify the law of conservation of energy as it pertains to heat. The second law of thermodynamics states that natural processes go in a direction that maintains or increases the total entropy of the universe. Entropy is a term meaning disorder. If you can conceive of a collection of atoms, as their temperature increases, they become more disordered, spreading farther and farther apart, as a gas would, perhaps in a hot air balloon, growing greater and greater distances from each other with more and more kinetic energy. Simply stated, things will become more disordered unless an action is taken to keep them in order. Thermal energy and temperature. Thermal energy is the overall energy of motion of the particles that make up an object. It is a distribution of energies within that object. Hot objects have more energy than cold objects, but not all of the particles have the same energy. It is an average. But any individual particle can have an extreme or fall within the range from the lowest to highest. We measure this energy as temperature, and it is measured on a definite scale. The higher the temperature, the faster the particles are moving. Greater average kinetic energy is the result. Temperature does not depend on the number of particles, but the average kinetic energy of all the particles. Again, if you can conceive of a bell curve, the kinetic energy of any object within that curve has a specific place, a distribution across the various energies. We conceive of the average temperature, or the temperature we read, as the mean of that particle distribution. Equilibrium is a discussion of how conduction is the transfer of kinetic energy when particles collide. They seek to find an equilibrium. It is when the rate at which energy flows from object A to object B is equal to the energy flow from object B back to object A, when there is no more potential for distribution of energy, when both objects have become equal in their energies, we can say that they are at equilibrium. Objects that are in thermal equilibrium are at the same temperature. Notice that this does comply with the law of entropy, the second law of thermodynamics, where once the energy was contained within one object, they have now spread over two objects, and there is more movement than before. Temperature scales. These were developed by scientists to compare temperature measurements with other scientists. The Celsius scale was developed by Swedish astronomer and physicist Anders Celsius and is based on the properties of water. Pure water on this scale freezes at 0 degrees Celsius and boils at 100 degrees Celsius. Each degree is an equal partition between those 2 points of 100 partitions. Temperatures do not appear to have an upper limit, as the interior of the sun demonstrates a temperature of at least 1.5 times 10 to the 7 degrees Celsius. But they do have a lower limit, a point at which all movement ceases. Absolute zero is the name for that point, where materials contract as they are cooled. If you cool an ideal gas to negative 273.15 degrees Celsius, it contracts and occupies a volume that is only the size of the molecules. In other words, all movement of the gas molecules ceases. There is no more kinetic movement. All thermal energy has been removed from the gas. It is impossible to reduce the temperature anymore. This, negative 273 degrees Celsius, is absolute zero and is the basis of the Kelvin scale, an alternative to the Celsius scale. 0 Kelvin equals negative 273 Celsius. Pure water freezes at 273 Kelvin and boils at 373 Kelvin. The temperature in Kelvin is equal to the temperature in Celsius plus 273 degrees. You may attempt some of the problems on page 278 in questions 2 and 3, and we will review these concepts as we begin our discussion in class of thermodynamics. Thank you for your attention, and I look forward to working out some of these problems with you.